Hi guys, so we're going to walk through a couple problems from acidic and basic salts. So the first of these, an aqueous solution of blank will produce an acidic solution. So what we're looking for here is our conjugate base of a strong acid. So in solution, when it combines with water, it will then form a strong acid on the product side. So we can look at A, that is a strong acid, so remember HBr is strong, but RbOH is also strong, so that will form a strong base, so that will be neutral. BaClO4 2, yes, there is two of them, but we will still have that strong base to help offset it. So we can get rid of that one. SO3 is not a conjugate base of a strong acid, so we can ignore this one. NO3, while being a conjugate base of a strong acid, K is also a conjugate acid of a strong base. And then E, well, it's the last one left, but ClO4 is a conjugate base of a strong acid, but NH4 is a conjugate acid of a weak base, meaning this one will produce an acidic solution. So all you have to do for this one is to consider each part of the salt, the anion and the cation, and consider where they came from. If the cation came from a weak or a strong base, then when it's back in water, it will also then produce a strong base. So really you're looking at where they could have come from. Were they part of a weak base or a weak acid, or a strong base or a strong acid, and then making your answers based upon that. And there was a slide in the last PowerPoint that detailed all the different examples and how you would know if they're weak and you're strong. So if there's still a little bit confusion with that, I would encourage you to go back and look at that one and just pause on that slide and really take a look at it and kind of try to walk yourself through it. Okay, so Kb for NH3 is 1.8 times 10 to the negative fifth. What is the pOH of a 0.1 molar aqueous solution of NH4Cl at 25 degrees Celsius? So let's start by writing our solution. So we have NH4Cl, and this is going to completely dissociate in water into NH4 plus and Cl minus. And we know we had 0.1 going in, but we also have 0.1 of each of these because it is complete dissociation, 100% dissociation. So we know we have NH4 plus H2O, well, NH4 plus H2O yields NH3 plus H3O plus. So what it told us is we have Kb. So that's when you're starting with NH3, when you're starting with your base. What we have is we're starting with our acid, so we need to solve for Ka. So remember, Kw is equal to Ka times Kb. So that 1 times 10 to the negative 14th is equal to Ka, which is what we're looking for, times Kb. So we get our x, which is equal to our Kb, or Ka, my bad, to be equal to 5.56 times 10 to the negative 10th. So that is what we will use. So we're going to set up our ice table, and we know that we have 0.1 starting here, don't care about water, 0, and 0, minus x plus, minus x plus x plus x, so this becomes 0.1 minus x, this becomes x, that becomes x. So with 5.56 times 10 to the negative 10th, that's such a weak acid that we can kind of ignore our x in the denominator, so we have x squared over 0.1. So we end up getting x to be equal to 7.45 times 10 to the negative 6th. And we know that that is equal to H3O plus, which we know means we can solve for pH. So I'm going to do that over here. pH is equal to negative log of that concentration of H3O plus, which gives us a pH of 5.127. We're looking for POH, so we do 14 minus that value, and we get a POH of 8.87, which is our answer. So this is a polyprotic acid question, specifically a diprotic acid, because we know sulfuric acid is H2SO4. So we are trying to determine the pH of a 0.75 molar solution of sulfuric acid. So what I'm going to first do, which is what you should always do for these questions, is write your equation. So we have H3O plus and HSO4 minus. So ice table, our best friend, we have 0.75, don't care about water, 0, 0. And actually, because it's 100% dissociation, we know at equilibrium we are going to have none of this guy left, but it is going to 100% dissociate. So our X is equal to our starting material. So we know after the first dissociation, we have 0.75 molar of our H3O plus. Now, the next thing that we have to do is we have to look at the second dissociation. So we have to use HSO4 minus plus H2O yields H3O plus SO4 2 minus. So we're going to do an ice table here. Initial of this, we have 0.75. Again, we can ignore water. H3O plus, we initially have 0.75. We've made some from the previous step, and we need to keep that in mind and carry it over. And then our SO4, we have none. So we have the change. So in this one, we get 0.75 minus X, 0.75 plus X, and then this one we get X. And we know our Ka is equal to 1.1 times 10 to the negative 2, which is equal to X times 0.75 plus X times 0.75 minus X. All right, so we know that our X is not going to impact it greatly. So in the bottom, we can get rid of it. So we'll get rid of it in the denominator, but we're going to keep it in the numerator. And the reason why we're going to keep it in the numerator is H plus is sensitive. So our pH scale is sensitive. So even if it's a slight change, we want to be able to detect that slight change. So for our H3O plus and for that value, we're going to keep it to make sure that we can see that change basically. So we get 1.1 times 10 to the negative second equals 0.75 x minus x squared over 0.75. We get this to be 0.00825 equals 0.75 x minus x squared. And then we will plug this into our quadratic formula. And after we do that, we get our x, and the only x to make sense to be x equals 0.01112 basically. So we can use that, plug that back in. Really all we care about is our H3O plus, so we want to see how that affects it. So we get our H3O plus final to be equal to 0.7612, and we plug that into pH. So we erase from over here for a second to give myself a little bit of room. And we get it, so pH equals negative log of our H plus, which we get 0.7612, and then we solve. We get the pH to be 0.119.